A while ago I built this robot, and many of its parts come from old 3D printers. At first it was mostly just a fun project, basically an overly complicated dog feeder. But working alone on projects all the time gave me another idea. What if the robot could become a main camera operator? To make that possible, I upgraded the main shoulder joint to a harmonic drive for smoother and more precise movement. And so the robot could follow me automatically, I added AI tracking. And to complete the system, I needed to integrate both cameras, the AI camera and the main camera, into one unified design. But before we can start, the old gripper has to go. So, let's start by fixing one of the biggest problems, the backlash in the main shoulder joint. One thing you can clearly see here is the play in the main shoulder joint. I'm using a planetary gearbox with a 100:1 reduction. Because of the long arm, even a small amount of play gets amplified. When I move the robot past a certain point, the arm drops forward or backward. The reason for this is backlash in the gearbox. To show that simply, here's a small gear model. When one gear turns, there's a short delay before the other one starts moving. That's backlash, and in this robot it's clearly visible. So the planetary gearbox has to go. To fix that problem, I'm switching to a harmonic drive. I picked this one up fairly cheap on AliExpress. It shipped by sea, so delivery took a bit longer. As you can see, it's actually quite small, even smaller than the planetary gearbox. The key difference is backlash, and a harmonic drive essentially has none. And the reason for that is this flexible gear. To show what's happening inside, I printed this open harmonic drive model. The main components here are the flex spline, the wave generator and the circular spline. The wave generator deforms the flex spline, keeping the teeth in constant contact. That constant contact creates a permanent load on the contact surfaces, even during load changes. In this model, the flex spline is made from soft plastic. In a real harmonic drive, it's made from spring steel, allowing it to flex elastically under load. Now, the question is, how do I connect the harmonic drive to the shoulder arm? The harmonic drive doesn't have a shaft, it only has a flat mounting face. That means I need a completely new coupling. You could probably buy something off the shelf. But instead, I designed a custom solution in CAD. To connect the harmonic drive to the shoulder joint without any backlash, I designed a 3-part coupling that locks together in a form-fitting way. It consists of a male hub and a female hub, with a flex insert in between. On my first attempt to bring this design to life, I 3D printed the parts to create a sand mold and poured molten aluminium into it. But the results weren't precise enough for this kind of part. So instead I machined boost parts on my CNC and finished them on the lathe. I have to admit, it didn't work perfectly right away. I went through a few iterations and had to remake the parts more than once to get the fit just right. What really mattered was a precise form fit with just enough flexibility through the flex insert.
Con esa actitud, dime dónde venden en la tienda alguien como tú, pa' que entiendas el nivel de tu altitud. Ey, dame el punto exacto de tu latitud, que no tenemos chance en la corte, ni un pasaporte pa' después de la muerte, así que fúgate con tu folklore.
Alright, let's put everything back together and see how the new gearbox and coupling perform. Before we start, the motor driver needs to be calibrated, so the FOC controller knows the exact position of the motor. And right away, something feels different. When I move the arm by hand, there's basically no play left, and when I drive the robot, it just holds its position. It doesn't drop anymore past a certain point, like it did before. The motion is incredibly clean now. And just for comparison, this is how it looks with the old planetary gearbox. Backlash everywhere. To figure out which camera we can actually use, we first need to know how much weight the new gearbox can handle. To find out, I'm going to push the system step by step, starting with 500 grams. At first, everything works exactly as accepted. Even at 1 kilogram, the arm still moves smoothly, both in the shoulder and the elbow. And even at 1.5 kilograms, it's still surprisingly solid. But as the weight increases further, at around 1.75 kilograms, the elbow joints start to give in. Basic movement and rotation are still possible. But lifting becomes unreliable, and when the stepper tries to compensate, it doesn't end well.
Nein!
So, that gives us a pretty clear limit. At around 1.25 kilograms, the system is still stable and reliable, with a bit of margin left. Now that we know what the arm can handle, we can choose a camera. Ideally, I go with the Lumage DH7, but at around 1.8 kilograms total weight, you can probably guess how that would end. So instead, I go with the lightest options available, the Sony QX10. At just 130 grams, it's extremely lightweight, and honestly, it just fits the robot perfectly. In order for the robot to follow me like a cameraman, it first needs to learn something very fundamental. It needs to be able to see. For that, I'm using a simple USB camera connected to my Mac Mini. Running on the Mac is an AI model called YOLO. It processes the camera image in real time and detects what's inside the frame: people, objects, movement. But for the robot to follow me, that alone isn't enough. It needs to understand my position inside the frame. And more importantly, how far I am from the center. So I take the detected person and calculate a single point right in the middle. That point becomes our reference. As soon as it's no longer centered, the code calculates the offset, how far I've moved, left, right, up or down. With this information, the robot can follow me. Not because I told it where to go, but because it sees me. For the first time, it's not just moving, it's reacting to what it sees. So, now it's time to install the main camera and properly integrate the AI system into the robot. So, why did I choose this camera? From a technical standpoint, it's honestly nothing special. It's over 10 years old, has a tiny sensor and only shoots up to 1080p. And you control it with a smartphone. So yeah, by today's standards, it's basically a toy. But it has a 10 times optical zoom, and more importantly, just look at it. Mounted on a robot, and it stops being a camera, it becomes a character. But will the image quality be good enough? We find out later. To properly plan the camera integration, I first need a 3D scan. For that, I'm using photogrammetry. I start by applying a matte coating to the surface. Yeah, a slightly risky move. Then I take around 50 photos from different angles and reconstruct the camera in software like Artec Studio. With a bit of cleanup, I end up with a highly detailed 3D model. And that's what I bring into CAD. The goal for this mount was to combine the AI camera and the Sony camera into a single futuristic housing, without interfering with the robot's kinematics. It might not look like much, but this took way longer than I like to admit. This time I'm printing the mounting parts in resin, hoping for a more premium finish. To give them a cleaner look, I decided to sandblast the parts. I never tried this before, but the result actually looks pretty interesting. I also printed the mount in FDM, just to have both options. And honestly, I kind of like them both, which only makes the decision harder. To assemble everything, I'm using threaded inserts, finally with the proper tool this time. Before, I was just using a soldering iron tip. To keep the camera head moving smoothly, I press in the ball bearing, which should make the motion a lot cleaner. Honestly, I'm a bit surprised myself how well the camera fits into the mount. I also prepared a small ESP32, just to drive a simple status LED. Maybe a bit overkill for a single LED, but I thought it fits the project quite well. And for some extra style points, I added a small Wi-Fi antenna. It doesn't really serve a purpose, I just like the sci-fi look. And just like that, it's finally finished. Now I just want to see what kind of shots I can get out of it. For the first test, I want to program camera move around this object. This camera move was programmed beforehand by manually moving the robot to different coordinate points and saving each position. To make that possible, I wrote a small tool that lets me record and replay the movement. As you can probably tell, there's still a lot of room for improvement. But hey, it works. And after that, I see how well the AI tracking can keep up. My expectations aren't exactly high right now. I mean, the camera is over 14 years old. So let's just see what it does. As you can see here, the AI detects me and places a tracking box around my body. Using that information, the robot can now follow me through the room on two different axes. One rotational axis and one linear movement axis. I mean, the footage doesn't exactly look impressive, but honestly, it works a lot better than I accepted. So, I'm really happy to finally be done with this project, even though there are still a lot of things I would improve in the future. But it's time to move on to new projects. So, thanks for watching the video all the way to the end, and I hope I see you again in one of my next projects. And don't forget to like and subscribe.